All right, and today we got the 20th. Let's see who we get at home. Okay, so our goal today, folks. We are live. I understand catalysts and what they do. And I got somebody at home already. Hello, Brooks. Welcome. So thanks the other day for joining me, everybody, in the Chem lab room. And I hope you like the demos. We're talking reviewing because I did them for a couple of reasons. And let me also give out some quizzes that I got graded. So here we go. This was the ground quiz.
Me the other way around. I know I did it right, but I got it wrong.
I did it wrong, like after
Okay, so I got Jonathan as well. Good, thank you, Jonathan.
-2.
Okay, so some of you can sit down. I'm not trying you to stand. I'm trying you to breathe. I'm not trying you to do it when I sit by. Okay. Questions about the quiz? We went over it right after we did it, so I don't really want to do the problem again. Some of you went really well, some of you really just couldn't do it. So you may get another chance in 10th grade or beyond, but I don't have time to reteach it because we have other stuff in the curriculum I still need to do. Like today, we need to talk about catalyst. You saw one last time. Do you remember I said there was a catalyst in which demonstration? Which demo had a catalyst in it? The elephant toothpaste. The elephant toothpaste, the last one. We'll talk about that one in a moment. Let's go back to the first demo I did, which was about paper and a block of wood. And we said I could more easily light the paper. Why? Why? Go. The higher surface area. Good. It's kind of like which of the three ways we said to make a reaction happen faster. So more surface area would be sort of changing which of the three things. Look at the three ways we had last time for making something happen faster. Go.
Wait, the three other ways?
We had three ways to increase the rate of a chemical reaction. So what I'm saying is, if we're talking about increasing the surface area of cocoa, that's like changing which of the three?
Add more molecules?
Yeah. So it's essentially, even though we're not adding more wood, if I make more surface area, then I have more of it exposed to In this case, it was exposed to what, David?
Oxygen.
The oxygen in the air, that's right. Good. Okay, I got a couple others that joined us online. Thanks, everybody, for joining us. Okay, poor quality. I'll try and read it off again, and I'll get you closer as I can, close as I can here, Brooks. So it says the objective is to understand catalyst and what they do. Understand catalyst and what they do. Good. Okay, I got also Tilly and UCN. Thanks, everybody, for joining me today. Appreciate that. Good. Got most of you. So that's dynamite. Good. Similarly, in the demo with when I blew the flower into the air, why couldn't I just light the flower with a match? Why did that not work so good, Matthew?
It had the surface area, so it was like, when you blew it was like a bunch of little things all apart from the rest, so they all got on fire.
Yeah, and they were all surrounded by what gas when I blew them into the air? David said it earlier, Stephanie? The oxygen gas, right? So in a sense, by increasing the surface area, it's almost like adding more molecules, isn't it? Here's a question. And it's not just so they look pretty. Why do they paint ships? How do they paint ships? Think of like a chemical type of reason. Yeah?
I mean, wood after a long time using.
No, sorry. Sorry, metal ships. I meant like a military ship.
Oh.
Yeah.
Well, but they don't rust because if they're in water for a real long time, they'll start rusting.
You got it. So what do they effectively, how does that prevent the rust, Keanu? What are they kind of eliminating when they paint it?
Well, I mean, the water doesn't touch the metal.
There you go. So essentially they're cutting down on the what? Math idea? By painting, Lisa? They cut down on the surface area. So painting, less surface area, and the rest of it, Keanu said, is exposed to the water. So, rust happens slower. So my point is, folks, sometimes you want a reaction to go fast, sometimes you want them to go slow. And rust is one they want them to go slow. So they decrease the surface area to make it happen slower.
Roasting is like a reaction, and in this case, it would be like instead of it being oxygen, it would be like the water that makes it react more.
Yeah, so that's it.
Yeah,
So
in this case, you want to prevent it.
you got it. Good. So you're cutting down on that water molecule touching the metal. Exactly. Coco.
I don't quite get the part with the less surface area, because if you paint the ship,
Yeah.
doesn't it still have the same surface?
No, there's a coating.
But like,
Yeah, but
metal.
It's between the water.
That was like
But
less
it's-
metal touching. I understand.
Okay, I mean, there's no metal touching it, it's all painted.
You're right. So it's the same surface area, Coco, but it's less of it exposed to water. That's what it's about. Yeah. Good question, though. I got another person. Let me add on. I got Marino. And I also had some answers here, and I didn't see them in time, Brooks. I'm sorry. Less oxygen is correct, and it doesn't rust. Yes, indeed. Thank you, Brooks. And I'll try to ask folks at home some questions, too. Sorry, I get a little forgetful at times here. Good. Marino, thanks for joining us as well. When we have a virus, we sometimes develop a fever. So this is not about whatever, this is about fever. So when we have a virus, we sometimes develop a fever, and now I want you to think of like a chemical reason why your body does that. Your body does that on purpose. Emelina.
I would think it's trying to kill off the virus by making it warmer, because virus maybe doesn't survive so hot temperatures or warmer temperatures.
That probably depends on the virus, but certainly making it warmer is, go back and look at the 3 ways to increase a chemical reaction. So what does making it warmer do? It certainly has to do with the virus, Aaron?
It increases the reaction,
Yeah, and the reaction is your body doing what?
fighting the virus.
Fighting the virus. So in this case, and that's a set of complicated reactions, but your body raises the temperature to make those reactions, as Aaron said, happen faster. So we want faster reactions that involve our body fighting the virus. And interestingly enough, it doesn't take a lot of degrees. Even if you get a slight fever of just a few degrees, that's a big deal. And it really makes it so you fight against the virus more. So there are some natural reasons we get a fever. Sometimes a fever is helpful. Not every time, but I would say most of the time. It shows your body's fighting. Stephanie.
Yeah, after that, most of the time your body is immune.
That happens too. And there's a more biological thing which we'll learn about from that, yeah. Good. Let's see if folks at home. Oh, I like the way of saying that. Menino says it speeds up the defenses. I really like that. So I'm going to put that in parentheses. That's a good way to say it. Speeds up the defenses that your body has. Defenses. Good comment. Yeah, exactly. Brooks said the same thing. Speeds up the defensive molecules in your body. They work faster. Julius is here. Thank you for joining us. A little late, Julius, but we'll put you down for now. Okay, good. Super. Okay. Do we use this word yet? Oh, question, David?
What is IX stand for?
RXN?
Yes, reaction.
Reaction.
Oh, yeah.
It's a R. Sorry, I raised the sloppy. RXN reaction. Okay. This is a pretty good term to think about chemically. It's called threshold energy. So threshold energy. The energy molecules need to collide hard enough and I'll see if you guys can fill the blank here. So let me read it off for folks at home. So threshold energy in chemistry, it's the energy molecules need to collide hard enough to something. And see if you can fill in the blank. I got one guess already. Hold on a sec. Coco, let's see if some others have time to figure it out here too. Energy molecules need to collide hard enough to, hey Mel.
Collide or?
Well, they're already colliding. It's in the previous part. So not just collide, but hard enough to what? to Aaron.
Produce reactions.
Yeah, or simply we can say to
React.
local.
Yeah.
Yeah. See if somebody had that. Nope, nobody had that online. Okay, so that's fine. I'll try and get you so you can see that, everybody online. Threshold energy molecules need to collide hard enough to react. Have any of you heard of this stuff? Online folks too. Yeah, Tully knew that. Thanks, Tully. What nitroglycerin? What is nitroglycerin? Matthew.
No. Oh, yeah. They use it in like dynamite and explosives.
You got it. It's a very, very high explosive. Do you know what phase it is? Solid, liquid, gas? That's okay. Do you know what it is?
I think it's in bottles, so
It's a liquid. So there's a high explosive called nitroglycerin. It's a liquid. And they used to have problems with it. In North America, they'd use it for mining. So it was to blow out rock. And just a tube of it like that could blow out a lot of rock. But on the way to the mine, it was carried on a wagon with horses. And what happened sometimes? It would explode because the little molecules would do what? Can you guess, Emelina?
They would be collided so hard that they actually react.
I want you to use the new word. Make everybody say that. Threshold. Threshold. Okay, so the molecules would reach?
Threshold energy.
All right, and then they could
React.
and explode, right? What do you suppose they started to do with the nitroglycerin to prevent that? What did they do to prevent it? Emelina, continue.
Maybe they packed it in so well that it wouldn't, whatever.
They tried that and it didn't work, and it still exploded sometimes. Another idea, Aaron?
Oh, that's right. Like packing in water. Or liquid.
Wait,
No, I don't know if they tried that, but that's not what they did. What else could they do? They want it so it doesn't reach the threshold energy.
maybe they added like a chemical or something?
They could do that, not to my knowledge, Emil, but they did something really kind of simpler for this,
Maybe freeze it.
Yeah. They froze it. And now it would thaw on the way to the mine, but still it was cold while it was being transported. And because the molecules are cold, how would they act, so to speak? Stephanie? They were pretty cold.
Well, they wouldn't.
Yeah, would they collide as much?
No.
And if they collided, would it be as hard?
No.
Right, exactly. So this was a pretty smart idea, and it saved a lot of people's lives to be able to then get it safely to the mine where they can use it to blow up rock.
It still sometimes explode.
To my knowledge, once they started freezing it, Matthew, they never had another explosion. As long as it was cold, by the time it still got to the mine, then they would let it warm up, and then they would use it in the mine. I'm sure there were probably other mining accidents. Well, what would you do? You drill a hole in the rock. You put in a test tube full of this stuff, connected to a detonator wire. You light the wire, run like crazy, get out of the mine, and then the thing blows up and a really huge chunk of rock comes out. So for its size, it has more blow-up ability than TNT. So it's really got a lot of ability. Questions, comments? Stephanie, then Aaron.
How do you spell nitrogen?
Let me write it on the board. I meant to do that and I forgot. Thank you for asking. So it's a liquid, high explosive. And for sure, you guys can guess it's got what's one element that's in it. One element that's in it, Keanu? Nitrogen. The other stuff you'll find out maybe in like 10th grade. So it's a liquid high explosive. Keep cool. So it does not reach the threshold energy. Okay, huge. Exactly. Yeah, the molecules broke, so they move slower. That's right. Then they don't hit as hard, and then they don't blow up. Yeah. Nice. So a lot of chemistry is pretty practical. That's what I like about it. Aaron,
Why did they move it in carriages?
that's all they had. This was back when the mining started in the mid 1800s. Yeah. No, I mean nowadays they could use it in the car, use it whatever. It doesn't matter. But those days, I'm sorry I didn't explain
I mean,
that.
they can still keep it cool nowadays.
They do, exactly. They still keep it really cool for the same reasons. So it's maybe less dangerous if you have a smoother road or whatever, but still they still cool it down.
How do they cool it?
Just put it in the freezer.
They just freeze it, and then they put it in a car that has a freezer in it.
They may do that today, yeah, probably, sure, yeah. In the old days, yeah, they just put it in an ice house and had it frozen, and things were good. Things were much more safe.
How do they keep the ice from melting?
I don't know if you know this, but they used to in the 1800s. They would harvest blocks of ice from the lakes. They even did that here in Berlin. They had big saws and they'd cut blocks like this big, and these guys would take them out and store them in barns, so like a shina in the winter. Huge blocks of ice all stacked up, and then they just cover it with hay. And if I have it out of the sun, Matthew, ironically, they'd still have blocks of ice left by the end of the summer. So it's very effective if you keep it all together, keeps it all kind of insulated in a barn.
There's also some people, they dig huge holes, and then they do it underground because it has
Yeah.
like the same.
Exactly, Coco, good point. Yeah, you can keep a lot of stuff cold if you dig a hole underground. It's called a root cellar back in North America. Keep your vegetables cool. And then they rot slower. So slower chemical reaction there too. Nice, let's make sure I got everybody, and yes, I do. Okay, I want to talk to you about catalysts now. So I'm going to erase this and point back to this first board. If my folks can see well enough. Folks at home, I'll try and say it a couple times too, in case you can't read it so well. I'm not sure how the transmission is today. Okay, we had something about catalysts the other day, right? I introduced them to you. Folks at home too. Tell me something about catalysts. What do they do? Amen.
They pretty much speed up the process.
Good. So they speed up, good. Speed up chemical, I'll abbreviate chemical reactions. All right, very nice. Speed up chemical reactions. Good. Something else about them? I don't know how far we got. Did I tell you something else about them? David, you remember?
Well, it's kind of the same thing as you said, but I mean, they make it more reactive.
Yeah, and they do different things, so I don't want to say like a blanket thing that's not always true. Something else about them, though, Stephanie?
Well, they increase the rate of a reaction without.
Yeah, that would be the same as speeding up the chemical reaction. They can be used over and over, so they're not used up.
They're reusable.
Yeah. There's a special type in the body. You might have this in biology. There are chemicals your body makes to speed up processes in the body. And they start with E. That's a good word for you to know. They're called enzymes. You ever heard of that? Enzymes? Enzymes are biological catalysts. I'll be right with you. Hold on a sec. So in your body produces a lot of enzymes. We're gonna see what one of those does in just a moment. Keanu?
Don't like break down your food.
Yeah, that's the one I was gonna tell people about. Do you know for fun the name of the one that helps break down the food in your mouth? Do you know,
Isn't it
Lisa?
like saliva?
It's in your saliva. It's in your saliva. So here's a little example from the example. So in your saliva, but it does what Keanu said here. In your saliva, you have amylase.
Ah,
Did you have that in bio?
yeah.
No?
Yeah.
Then you're just pulling my
Naturally,
leg.
happiness is you.
I don't know.
Yeah.
Keanu, do you know what special stuff that you eat that especially this breaks down? Yeah, the type of sugar we call starch. And it breaks down the starches into what we call simple sugars. And you'll study those in 10th grade, Lauren. Yeah, so whenever you start to eat something, your body produces more of this as you eat, and it gets mixed in with your saliva and it breaks down the food. If it didn't do that, believe me, it would take a lot longer for your food to break down in your stomach. So enzymes are good. Your body makes tens of thousands of different ones. We're like a chemical factory. We make all sorts of stuff like that. Yeah, Marina knew that. They break down starch. Good. And Brooks looked up a catalyst. Yeah, it lowers the amount of energy you need. Good. Brooks, we're going to come back to that probably next week when we talk about diagrams. And remind me of that, Brooks, when you're here. Okay, so here we go. Aside from biological catalysts, we got two types of catalysts. And how are we doing? We're going to get one in. Or at least talk about one today.
What's the one that we used yesterday?
The one we used was iodide. So it was I minus, you know how some can have a charge? So this is and iodine, anybody remember for fun what family was iodine in? Or what column? What do we call it? Group. What group was iodide in? You remember, Coco?
Alkaline earths?
No.
No?
No, it's not in the
Oh,
alkaline
yeah, right,
earths.
it's not.
It's, Lisa's probably found it. It's where?
In the food? No, in the.
It's a family with F, but it's got a special name. Somebody else, can you remember? The F family starts with an H. It's a halogen. Thank you, Stephanie. So the iodine takes a minus and then it's a halogen. So we saw it working yesterday. That's what made the toothpaste happen so fast and broke down what's called the hydrogen peroxide. Be right with you? There's the one I want to do first. Yeah, you may. Okay, so the first type is called heterogeneous.
That heterogeneous in German?
Yeah, heterogeneous. Yeah,
But you said heterogeneous.
heterogeneous. Yeah. So let everybody say that word, please. Heterogeneous.
Heterogeneous.
Good. And what it means, well, what does hetero mean? Hetero means different. So it's a different phase than what it works on. Different chemical phase than what it works on. And remember, phase is solid, liquid, or
Yes.
gas. Good. Oh, see, a couple of these guys knew halogens. Thanks, Marino. And Tilly knew that too. Good. Well done. The example I want to give you is in cars. And I mean cars that burn benzene, regular gasoline, we'd say in English.
I think
So not electric cars.
Diesel.
it's will be so as well.
Yeah, and cars that use diesel as well have a catalyst in there. Now, the catalyst, I'm going to give you the name in German. Yeah, that's it. Is it with the Z? I think it is. Does that look like I spelled it in German right?
I think it's with an S.
Yeah, I don't think this will be
Katalysator. Thank you.
right on that.
And somehow I think it starts with a C, but in German it could be a K. I think it's a C.
Yes,
Katalysator.
probably everyone that has it too much I know, but.
No, I think it's.
You know what? If somebody could, pull out a phone and Google it and let me know how to spell it.
Yeah.
All right? Katalysator. I'm going to give you the words in English. You ready? In English, it's catalytic converter. So in English, it's two words, catalytic converter. In German, we just say Katalysator. You might have heard of it. Do you know what it does? For fun, what does it do? Coco.
It filters some of the Schadstoffe
Yeah,
out that the car produces.
you got it. So the stuff that the car that comes out of the car, the Auspuff, or in German we call it no, that's the German word Auspuff. English exhaust. The exhaust comes out of the car, and yeah, Coco's right. This tends to.
It's spelled with a K or like a Y.
Okay.
Oh, it is a K. Katalysator. Ah, wow, that's good for me to know. Okay, so let me spell it correctly. Check it for me, Lisa. Does that look right now?
Wait, yes.
That's it. Okay, I'm going to write it in my notes for next year in red to make sure I have it right in here. Katalysator. Thank you, Lisa. Okay, so we know it in English and German now. Yeah, so it cleans up your exhaust. And let's see how it does that, okay? So, where do I want to do this? I really need more room, so I'm going to do it over here. Let's make sure folks can see that at home. Let's erase a little bit.
Open the door as well.
Yeah, I could, although the inside last time I looked was so messy. Look at that.
Or you can write on that one, you can write.
Yeah, I could, but that's pretty messy too. So I'm going to limit myself because I also want the folks at home to be able to see this, right? Gentlemen, let's not keep looking at each other. Really, that's enough, right? Okay, so draw yourself the exhaust pipe. Think of like a pipe with the exhaust coming out of the back of the car. Let's say it's coming this way. So here comes the exhaust. And what's in the exhaust pipe is a grid. And I'm going to show it like this, even though it doesn't quite look like this. And the gas has to go through it. The exhaust has to go through here. Okay, that grid is made of just iron, but it's coated with another metal that's really expensive.
What is it?
You tell me. Give me an expensive metal. David, give me an expensive metal.
Cool.
Gold. It's not gold. More expensive. Give me another one.
Platinum.
Platinum.
But like really thin, right?
Yeah, really thin. But even though it's just sprayed on platinum, it's the most expensive part of the car. So if you take an old car to what we do in America, take it to the junkyard. First thing the person at the junkyard does is they get in there and take out the catalyst off it and send it in, and somebody reuses the platinum because it's so expensive. Platinum's a lot of money. So that's several hundred euros just for that little tiny screen bit of platinum that they put on there.
How much is like 1 gram of,
I don't know the market price anymore. We'd have to look it up. But it's about just higher than gold, right? So higher than gold. Okay. What's some stuff that maybe you know this? What's some stuff that is in the emissions that Coco talked about? Do you know anything that's bad that you don't really want to breathe it? CO2 is actually not so bad. We exhale it. It's not good for the earth, but when we breathe naturally, we actually exhale it anyway. So that's not really a problem. But there's another carbon stuff that's a problem. CO2 is not poisonous, but there's something close to that that's a poison for the body. Do you know what these things? Yeah, so carbon monoxide. So carbon dioxide has how many O's? Di is? What's di stand for? 2. So CO2, carbon dioxide. Carbon monoxide is CO. Let's have that come in. So let's say there's some CO molecules coming in. Anything else you know? Monoxide. CO is carbon monoxide. Mono is like 1. Carbon monoxide. So it's a poisonous. So you can imagine. You imagine that it wants to get cleaned out. We want to clean it out before we let the exhaust out into the air. Yeah, so CO2 is not the problem, but CO is a problem. Any other gases you know that come out of your exhaust that aren't so nice? I don't expect you to know this one. The other one is NO2. So 1 N and 2 O's, NO2. You guys know it as the color that makes the air brown in the summer sometimes. What's dirty air called in cities? Small. Yeah. So this one it makes small brown. So it gives the brown color to smog, so it's not very nice stuff either. Okay, let's see what happens. So I'm just going to do NO2, so I'll do CO, but NO2 does the same thing. Okay, I know I haven't used a lot of actual chemicals till now to talk about things, but believe me, you're going to get this because you know about the periodic table. What were the two sides of the periodic table? The side and the side. What was on the this side and what was on this side from your point of view? Emil.
Metals and the non-metals.
Exactly. Good. Which one wanted electrons? Wanted more electrons? Metals or non-metals? Which ones wanted more electrons? You remember, Kiana?
the metal?
Second guess? The non-metals. Remember, they're lacking electrons. They want to get the same amount as what family? What's that last family, Keanu? The noble gases. So the last few families, they really want to get that, including C and O and N. They all want electrons. Okay. Metals can do what with electrons? What could that side do? The non-metals wanted electrons. What could the metals do? Stephanie? They give off electrons, including our metal, our expensive metal, platinum. So here are these nice electrons, right, on the platinum. And what does the CO do? CO goes, oh, look at that electron, and it lands there. So it lands on the how should I say this? It lands on the wire that has the platinum, if you can write it in there. And by luck, let's say another molecule comes in and hits this. You ready? Another molecule hits this, a molecule called O2. Bam! Break apart. Remember chemistry we said is breaking bonds and making bonds? And now something reforms out the other side that is less poisonous. What could maybe, when CO hits O2, how could they reform and make something less poisonous, Aaron? Not easier than that, CO2. So here's what I'm trying to show you, okay? Remember that word threshold energy? Well, the amount of energy needed if the CO lands on the little wire is a lot less. So here comes the CO, right? I'm going to go over to the piano here. Here's, let's say that's the wire. Here comes the problem. So the CO says, oh man, electrons, nice. And it lands there, and suddenly it's a lot easier for the O2 to come in and go break it apart, and then reform it into CO2, which of course is less dangerous for your body.
But doesn't platinum run out of electrons?
That's a good question. The answer is no. Electrons, there's so many in the world that they just flow in and out of the car. It's not really a big deal. The same thing happens with the NO2. The NO2 is also nitrogen really wants electrons. So here comes the nitrogen. Maybe it lands down here. And here comes another O2. Slamobama. Slamobama. Pow! And because the NO2's landed, it's a lot weaker, the bonds. And the O2 can split that sucker. It's a lower threshold energy. And I get something coming out the other side, which is N2 and more O2. And you might know that a lot of air is naturally made up of anyway. What does air have in generally anyway? David? Now, and nitrogen. Air is mostly nitrogen. So that's not going to hurt you at all. So these guys are non-poisonous. So the platinum, PT, can we write that? I bet you know what that is. That's platinum, right? The symbol for platinum. PT allows CO and NO2 to break up easier. And other than the electrons, have I lost any platinum? No, the platinum doesn't get used up, so it can be used over and over and over. That's why it's truly a catalyst. P2, PT, and the PT platinum used again. Go.
So these catalysts, or the catalysts, they're so long. So do they have more than one of those grids in there?
No, and to be honest, can I tell you how it really looks?
Yeah.
It doesn't look like this. It looks more like a honeycomb.
Oh.
So actually, it goes through a longer amount of space, but I can't really put that on the board because it's three-dimensional. So the gas goes through the honeycomb and it comes out the other side, and it's not 100%. There's still a little bit of these bad guys left, but a lot less. So catalytic converter cleans your car pretty well.
But how poisonous is it? Like, is it like about the platinum thing when you decide to use that?
No, but you'd be polluting. Before they had those, David, before they had those, cities were a lot more polluted. And they had a lot more people with lung problems. So it would cause long-term problems for people's lungs. That's a good place to stop, folks. We'll do the other catalysts at home next week. We'll see you guys at home. We'll just the live stream, so join me for each class next Tuesday and Thursday. Thank you, Amy. Bye-bye. Thanks, everybody at home, for participating. We'll see a lot of you next Tuesday. Here.
Like and subscribe.
Yeah, like and subscribe.
Subscribe to my channel.
Not required.